working our design pieces on the design of water sewerage irrigation systems in the Rowan City residential complex. First, we would like to give a general overview of what we went through and what we go through the application. An introduction, a brief introduction, detailed details of the water distribution network and the sewage system in terms of design criteria, components of the water network, design steps, results analysis, and optimum design. And of course, we will show the remaining objectives for our design and the time plan and the rest. As an introduction, our objective was to design the water distribution network, design the sewage network, design the irrigation network, and the structural design of the irrigated tank. Our proposed design differs from the original design concept in the way that we emphasize on the concept of water usage rather than water consumption. In the original design, the irrigation demands and the residential demands are both supplied by fresh water from the Sewerage freshwater network. In our proposed design, irrigation demands will be supplied by treated water from the sewage system itself, so we will reduce the demand on fresh water. For the water distribution network, our design criteria, the fresh water supplied to the complex is supplied at an elevation of 97 meters above sea level, and the maximum pressure head of 4.2 bars and the minimum pressure head of 3.2 bars respectively. The pipe velocity has to be less than 3 meters per second to avoid abrasion to the pipes. Pressure range for all the junctions and in the residential complex should be between 2 and 5 bars. The fire demand, according to the code, would have to be satisfied at 25 meters per second at all junctions with a minimum residual pressure of 2 bars. And of course, the minimum cover for the pipes below the ground level will have to be 1 meter to avoid any damage to the pipes due to live wells. The soil type for our complex in general is a type of sandy soil. So UPVC pipe material is found to be suitable for this type of soil. The components of the water network. The water network is composed of a transport pipeline from the source to the network itself, the main pipes in the network, and the sub-main pipes or the second pipes, the elevated tank, and the isolation valves. For the elevated tank and the isolation valves, they were not put into consideration from the beginning. We will still comprehend and we need them or not. This will be more clear as we go through the alternatives in the design. The first step in the design is to lay all the main pipes and the secondary pipes. In this, you can see that mainly the main pipes will be the boundary pipes around the complex. They will be at a diameter of 200 millimeters, which is the main loop in the system. The secondary pipes that branch out to the middle of all the areas are at a lower diameter. The second design step is to estimate all the population in the complex, because we need to estimate essentially the total demand for fresh water. So for the complex, we have 293 villas, assuming the 10 capita per villa according to the code, and 203 buildings with 16 apartments per building, with an assumption of 5 capita per apartment. And of course, a commercial area that is calculated, estimated in terms of population according to the code that gives us 75 capita per hectare for commercial area. After calculating the total population, having had already known the number of villas and buildings, we can estimate the total population of the community, which is around 70,000 persons. The code, the Egyptian code for sanitary and water works assumes that the average daily demand of one person per day is 280 liters. Multiplying that by the total population, we get that the community needs an average daily demand of water of 5,660 meters cubed per day. This is the average demand of the community over the whole day. For the peak hourly demand, the factor peak hour demand is at the time of 12 hours work in the noon. It is a factor of 1.4 of the average daily demand. Therefore, we have an average daily demand, peak hour demand for the whole community of 7,124 meters. This is the initial layout or the model that we inserted in the sewer water gems to resemble the actual layout of the pipes in the compound. Of course, you can see for the pipes, the nodes, they are imaginary. The nodes don't actually exist in the real situation, but they resemble the demands that are needed from each pipe. So this is the initial layout. The pipes, of course, are laid under all the roads, the main and secondary roads in the.
Okay. We did analysis for we did the steady state analysis on this initial model. Okay, and here's the result for the steady state analysis. As you can see, there is a pressure, there is a color code for the pressures, which shows that there is a range for the pressure according to every color. As you can see, the green color shows that the pressure is between 5 to 2 bars, and this shows that on the steady state analysis for this initial model, it's okay. The pressures are within the criteria for 2 to 5 bars. And as you can see, also the pressure contours are all in one color, in the blue color. It shows on the top left that the pressures are maintained between 5 to 2.5. Okay, this is for the steady state analysis, which analyze the system on the peak hourly demand. Okay, and using the maximum flow. Okay. Another analysis is the extended period simulation analysis. It analyzes the system over the 24 hours, okay, and gives us the pressures at different times. Okay. As you can see, the pressures in the whole community stay within the allowable range, except for this low elevation zone. This area has a low elevation zone other than the whole community. So what happens is that at night, during the evening, when the demands are low, okay, and the head loss is minimum, the pressure head is maximum. And that's why during the evening, the pressures in these junctions, in the red and the black color, exceed the allowable range. Okay? So what we did is, we have the first alternatives to use pressure reducing valves and in the pipes that feeds this low elevation zone that has high pressure. Okay? So we put these pressure reducing valves and we adjusted the diameters, and after many iterations, okay, when we played the APS for this model, you can see that the pressures are all green, except when it reaches the evening. At the end, we have only 2 junctions, okay, that exceeded the 5 bars. Okay, this is so the pressure reducing valves approach has still some concerns. First, that still we have two junctions that did not meet the criteria, and second, the PRBs in general are costly and need frequent maintenance. They did not last for the whole design period of the project, and it causes the waste of energy available from the main source. Okay, because it reduces the energy count, the water energy count. So our next alternative is that we separated the low pressure, the low elevation zone, which has high pressure. We separated it from the rest of the compound. You can see here is the separation for the network. Okay, and only these pipes are connected, but they have a closure valves that are by default closed. They will only open in case of emergency. I'll explain that later. Okay, this low elevation zone where the high pressure will be fed only through an elevated tank, which will be stored here. Okay, this elevated tank will be collecting the water from the whole community. Okay, and then the supplying water to this part according to the demands. So in the morning, the tank will be supplying water, will be emptying and supplying water to this area, and during the evening it will be filling, and when the demands in this area is minimal. So it acts as a balancing tank, and thus it reduces the pressures in this area. When you see the EPS on this alternative, you can see that the pressures stay constant all over the day, because the tank is having this balancing effect. Okay. Another benefit of this elevated tank, which has storage, which has the water stored at elevation, okay, that it can be used in emergency. In emergency, when there's a supply cut off, okay, from the main source, these isolation valves will be open, okay, and the tank would be able to supply the whole community with the water stored in it, okay, for almost 9 hours, as you will see later in the graph. So that graph has percent and volume full over time. Okay, as you can see, during the evening the tank is being full, and then it starts to decreases and then increases to the same level over the day. Okay, according to the demands. This graph is inverted. Is the reflection of the pattern. Here the demands, when the demands are minimum, it's filling. When the demands are maximum, it's empty. Okay? And this is when the isolation valves are open in case of water supply cut off. As you can see, if the tank is full to 100%, it can supply the compound for almost 12 hours. And also we did find a 5-flow analysis on this model. The 5-flow analysis, it takes the fire demand at at all junctions and tests the model for certain conditions, like the residual pressure should be maintained not less than 2 bars, and it has the result saying passing or fail, the whole pass. So we have the elevator tank. So elevator tank was very important. It acts as a balancing tank, it acts as an emergency tank. If you use the pressures, it was
okay, now we move on to the next scope of work, next part in our scope of work, the sewerage network. First of all, let me talk about the cycle of wastewater. We start by collecting wastewater through the sewerage network, and then by gravity, and then we move it to the pumping station and pump the water to a wastewater treatment plant, and then we use the pumping station again to transport the treated water to cover the irrigation need of the irrigation supply. Now, for our modeling philosophy, there were several factors that we had to consider before building up our model. The first one was collecting the sewage by gravity. Of course, we have to collect sewage by gravity to avoid for instance, if we had our flow pressurized, that would cause abrasion to our pipes through the depositions in the flow. And then we have the second thing we had to consider was the combined system. Our system is combined that accounts for wastewater discharges and rainfall consideration. And then we have to consider the location of manholes. At each road intersection, we have to put a manhole. At the change in slopes, we have to put a manhole so as to account for the new slopes for the sewers. And then we had sometimes we're restrained to use start manholes, and that was at the points of high elevation, so we can distribute the sewage by gravity. And then we also had to create another manhole based on the change in the diameter and then change in the piping. Now, the location of the pumping station is basically at the lowest point of elevation in our and this is to be able to collect the whole sewage by gravity to that point. So basically, it's the lowest point. And then the location of the wastewater treatment plant. We have to locate the wastewater treatment plant at the place where the wind will carry away all the undesired smell or anything produced by the wastewater treatment plant, so it won't go to the residential areas. Now, for our design criteria, the velocity range was the minimum velocity was 0.45 meters per second, and the maximum velocity was 3 meters per second. The lower than 0.45 meters per second will cause settlement and deposition of the settlement of deposition will flow, and the higher velocity will cause abrasion to the pipes. Now, our slope range, we had a minimum slope and a maximum slope. The minimum slope is usually 1 over the diameter, and it is the slope that will guarantee that we won't go beyond or lower than the minimum velocity, and the maximum slope is the slope that will guarantee that we will exceed the maximum velocity. Zero diameter, we were restrained by the Egyptian code that we cannot use sewers less than 200 millimeters minimum depth. When we were restrained to use third input level of manholes, the minimum depth we had was 1.2 plus 1.2 as a cover plus the diameter of the sewer. The maximum depth we had is 6 meters. And this maximum depth is to ease the cover fill and to ease the construction method for the contractor. The last thing we have is the part material. And again, we use the PVC part materials because basically they're highly resistant to chemicals or anything during the flow. They have a low weight and they're economically good, they're cheap. Now this is our model. This model is with the contour lines to illustrate our modeling philosophy. At this point, as you can see, this is the highest elevation. Here we are restrained to use these dark manholes so that we can distribute the sewage by gravity. And at this point, it is the lowest point, and this is where we had to create our pumping station. Now the pumping station pumps the water all the way to the wastewater treatment plant using a force main, and then we use another pipe to cover up the irrigation needs. Okay. And I'm sorry, here is the north direction. So basically, there is the wastewater treatment plant, and the wind coming this way to take all the undesired smell away from the residential areas. Now, this is the profile of our main trunk sewer. this sewer is actually from this point to the lowest point. As you can see, the green line above is the road slope, and the blue line, the road slope at the ground elevation, and the blue line is the inlet level at the sewer elevation. Okay? The distance, the difference between the ground level and the inlet level is now depth. And then, as you can see, all the slopes are going downwards, so that we can collect the sewer by gravity. And at some areas, as you can see, the slope of the road will go upwards, but we're restricted to move the flow in that way, so we use the minimum slope so as to collect the sewage again by gravity. And sometimes here at connections, we have different inlet levels, so as you can see, there's a problem. Now, Muhammad Hashmawi will continue with the detailed
moving forward to the design process, we need to determine the location of the manholes and discharge per capita, calculate the peak factor for the minimum and the maximum discharges, calculation of the inlet levels at the start of the end manholes for every conduit, and the inlet levels, the minimum inlet level for each and every manhole. Then, using the assumptions of the diameters, we'll be able to get the minimum slopes and perform several iterations as much as possible to reach the optimal design. According to the Egyptian code, this is the factor for the maximum peak. This is how we look at it in the software CAD. This equation allows different codes with different values to change these numbers to reach the equation of control. And the same is applied for the minimum structure. Okay, in order to calculate the inlet levels, which was the most challenging part of the sewerage, I take this connection as an example. This is manhole 1 and manhole 2. The elevation here is 97. At the start manholes, we usually subtract from the ground level elevation the 1.2 as a safety for the pipe, multiplied by the diameter of this sewer. To calculate the inlet level at the second manhole, we need to subtract the inlet level of this manhole. We need to subtract the slope multiplied by the length from the inlet level of this manhole. And this will be also performed from this sewer, which is coming towards this one. And for this manhole, we choose the lowest inlet level calculated for both sewers. This is the profile. This is conduit point. The ground level is indicated in green, and the difference is the color between which and the blue. The inlet level at manhole 1 is 95.6, and it starts increasing when it reaches the base of the manhole here. And this drop shows that the inlet level coming from the other direction was lower than the inlet level from this direction. Therefore, there is a drop starting from the minimum point. In order to change only one manhole in the CAD, we need to recalculate all the inlet levels of all manholes. Therefore, we develop a user interface where you have the inputs, these are the inputs, and you get the inlet level on the cover to ensure that you're not against the safety regulations. And the same thing is done for the conduits. And this is after doing several iterations in which we able to reach this optimal design for the network. The ground sewers indicate that the velocities between our range over 45 to 3 meters per second, and only the start manholes the start sewers had issues in the velocities, which was less than the over 45, because that makes sense because still we didn't collect many discharges as the other ones. These are the results obtained from CAD. The last one shows the percentage full of pipe in the sewer. This is for the minimum scenario. The number of pipes, number of sewers with less velocity, less than minimum velocity increased, because this usually occurs at night time when there is no discharges. And these are the results obtained. So we need to get solutions to fix that, to avoid any settlement. So the three main solutions, either using flushing tanks at the start manholes, or regular routine maintenance, or use cars that flush water at the start of the day, and they usually known as the full cars. This is the most optimal one and the most commonly used. The accomplished work will then be able to finish these advanced design of the water network and choose the most optimal design. And a great tank. We finished also the advanced design of the sewerage network pumping station. So we still need to work on the advanced design of the pumping station and the post main. We need to calculate the irrigation demand to know if the amount of water that will be treated will be enough to supply the irrigation or will be more, so if we need another post main or not. And the structural design of the irrigated tank, and by the next presentation we'll be able to provide you with all the design drawings for the water areas. This is our time plan, the initial time plan. You're still schedule. You're up to here. We finished the design of sewage network and go about the water network. We're only late with the pumping station, which will not take more than 2-3 days. These are the references that we use.
You have lots of friends.
For the sewage system, what is the relationship between the pipe elevations and the road elevation?
No, there is no relationship, it's just on something.
Sorry?
There is no relation between the road slope and the calculation. It's just extract that number to ease the way of estimating the relation slopes.
Yeah, well, I mean, you need to find out if it is reasonable. I mean, you come up above the road level, for example.
That's why we make the cover. The cover, which is the difference between the ground level and the inlet level. If this cover is greater than, is less than 1.2 plus the diameter, we need to have a drop manhole, and we repeat the same story.
You have a maximum?
We have a maximum. Yes, we have maximum 6 meters.
And you
Okay,
are
otherwise, we need to have a pumping station, and that will not be cost efficient.
So your network is within these two numbers.
Yeah, yes.
Are you going to design the treatment station?
No.
No.
When we know the house, we don't have much time for that, and we only calculate what will be treated, the amount of water, and use the irrigation.
Are you going to have enough flow from the wastewater to make the irrigation?
This is what our challenge we're going to see after we calculate the irrigation demands. So if the flow is less than the irrigation demands, we need to have to increase the water network, some extra water for the irrigation to help with the treatment. If less, we need to have another post line going directly to the Sheikh Zayed main sewerage network, and we only supply the wastewater treatment with the amount of water needed to supply the irrigation.
And the water demand you had per capita or water supply, do you have any other needs for the water? Sorry? You make the needed amount of water per capita, right? That's a household use. Do you have any other needs in the resource other than that, household needs?
We have the commercial area, which has the balance.
Did you consider that?
Yeah.
We converted the area, the commercial area in terms of an area into a number in population terms, which is 75 capita per hectare. This is
Actually, we are taking 1 hectare, and this is from the whole 75 capita per hectare. It converts it to capita, so we can add it to the number of people as the whole community.
What is the difference between your design and what is already constructed there in terms for the water network?
The actual design has a ground tank and a pumping station, but our design has an elevated tank that distributes the water.
This makes use of pressure. This makes use of energy and the pressure head that has been coming.
What are the advantages and disadvantages of yours against actually
We are using the elevated tank, so we are not wasting the energy, keeping the water stored at elevation. That can be, it's doing the function of balancing as the ground tank, and it has an extra benefit, which is storing the water at elevation so that when there's a supply cut off, it can resupply the whole community.
We're not depending on the electricity from the pumping station and the ground reservoir in case of fire.
And
there's an electricity cut off in case of fire, we'll be able to meet with the fire demand. So a high level of standard.
convince the developer that your system, which is more costly, is better than their system?
Yes, this is a higher level of service.
This depends on the level of service. The safety. More safety design.
I'd like to add one thing. The initial design is a direct feed one. The main disadvantage is there is a cutoff for the main source, and there will be no water absolutely for the compound. Certainly, the developer will allow this to happen for even 1 hour. The there has to be an elevated tank that with a certain capacity of storage to supply the network for a couple of hours. In our case, 6 hours, around 6 to 8 hours. There's a cutoff at the main source, so I think it is worth it to establish an elevated tank for this safety reason.
I think if you see a balancing tank, how can a balancing tank reduce pressure in a low pressure, in a high pressure zone, in a low pressure zone?
Because it's
Any balancing tank can do the job, or can you do something to make this happen? Because a balancing tank, by definition, does not reduce hydraulic very much.
it's the fact when the area that has pressure, that has high pressures, when the demand is decreased, the elevated tank will supply only the demand needed. So it's filling.
What I'm saying is, if I constructed this elevated tank at any elevation, it would still, and it can still act as a balancing tank.
No,
It still solves the problem.
because we chose the hydraulic gate line to reach the maximum above the junction it supplies to, and a minimum below the junction it supplies to also. So it's always
Maximum.
the flow is always supplying to the
Is your
according to the demand.
elevated tank, is that conventional one, or your piping connections to it are different from usual?
You have a pipe inlet
You
and
have to control pressure, not only to balance supply and demand.
No, but certainly it's not. This tank has a different piping connections than the normal conventional ones, according to the model in the water gens. It has a different the inlet tank, the inlet pipe is different than the outlet.
Another question, why do you use GPS?
Sure that they
Without using GPS, can I just design everything as designed? What is the added information you got from GPS?
Yes.
EPS analyzes the demands in different hours, so we have to be ready for the supply in different hours based and different demands to account for different pressure.
I would like to add. In the steady state analysis, it considers the maximum flow. Okay? So when the maximum flow, when the pressures are not that high, the pressure head are not that high. But during the evening, when the demand decreases and the flow is minimum, the pressure loss is minimum, and the pressure head is maximum. So the EPS allows us to consider the Q minimum and the Q maximum and the pressures in both conditions.
Use the peaking factor, a maximum peaking factor, a relevant peak hour demand or peaking factor. Okay? And to size the pipelines, will your results differ than if you use the EPS in your design? What is the main element that require EPS simulation in your water?
It's the main element.
Yes. In your distribution network, you have many pumps, you have reservoirs, you have pipes, you have fixtures, you have valves. What are the elements?
اوعى تكسب 2000 جنيه في استبك الرجاله.
EPS is especially important for the EPS pattern, especially important for the design of the tank.
Now, your wind direction will make all the small bottles of the away from the community.
To the community.
Into the community.
Why?
Because it's coming from the closest where the people bank side towards the community.
The wind is coming from northwest. It's coming almost to the
I'm
community.
just looking at your arrow and it's basically shuffling all the other trees that are there. Yeah.
North is in that direction.
Anyways,
We did not put the north direction on the AutoCAD. It was given to us. The AutoCAD, the data that we collected from the, we can shift. We can shift.
No, I'm good.
I have a couple of questions. This is not my area, but what are the kinds of pipes available in meters? Because you mentioned pipes that you use UVC because that and because this. What are the kinds of pipes available? Sorry?
Clay.
Aha. What else?
Steel.
Rock? Did you hear about GRP? So why didn't you think about that?
I think it's more expensive.
Is it?
UPVC is generally
Okay, so that, I was hoping that you are going to say yes, you are going to design the STP. But you answered to your top one, this is not in the
Wastewater treatment plant.
yes, it's sewage treatment plant.
We have a lot of
Yeah, but your project will be complete by this design.
Model. We're going to choose a complex model, and we are going to design the hydraulic. We're going to find the hydraulic design of the wastewater.
These are hydraulic design of the STP. I'm not saying
yeah,
section
yeah.
design. The hydraulic design of the STP should be there. Yeah. What is the depth of your pipe? Oh, sorry, of your pump. Yeah, you mentioned that you have gravity pipes and this. So how many pumps do you have? You have just underneath. So you're going to use pump underneath that. You're going to bring the water the right way.
Yes.
Or you have two pumps.
I still did not design the pumping station for this.
No, I don't understand that. You're going to use the pump, okay, to pump the water.
Yes.
You pump the water horizontally or you lift the water and using another gravity pipe. What are you going to use?
We use the pumping station to pump the water from this low irrigation area to the place of the wastewater treatment plant where we can.
Oh my God, so you are going to use the pump and you have pressurized pipe from this area up to the sewage treatment plant, you need to reconsider. Usually we have, I don't know about that design, it's not my area, but you have two pumps, right? One which pumps the water there, then the other one or other factors so that you collect the water, and then you need gravity again to the STP.
Well, the thing is that the pumping station is located at the
lowest
elevation of
elevation.
73 meters.
They told me it's not my area, so please, just study it again.
Justify why you have to use pressurized pipe to transport the sewage back to the treatment. Why a gravity pipe cannot work?
Because this is the lowest elevation.
This is high
We're constrained to have the
This is
wastewater
about
treatment
97
plant.
or 95 meters above the
So
sea
you
level.
have pump here, right?
Yes, we have the pump at this
So
position
the
exactly.
purpose of that pump actually is not
The
to
ground
give the
level,
water.
ground level.
The purpose of the pump is to pump the water in pipes up to the STP.
Yes, here is STP.
Oh, so it's short distance. You mean.
Yes, the elevation here is 95. The elevation here is 70.
So I mean,
there's no way to make it
your
work.
estimation is short distance.
It's short.
So this is you. This will be UVC pipe with pressurized
No,
water.
no, we said for the sewerage method. We didn't say this will be the most common. I'm not sure.
Think about GRD. Okay. One last comment. I was lucky to see go to work with Dr. Ahmed Shafai in the design of STP and Kuwait, which is half million meters per day. Okay. And you mentioned something which, if you hear it, you will have a heart attack. You said you are going to put the sewage treatment plant away from the complex in order to avoid the smell. If you have a smell from a sewage treatment plant, that means you failed. It shouldn't give you any smell. Even the sludge tank, the sludge removal tank, it's contained. Doesn't smell. Okay, don't mention that. This guy here really had a heart attack. Thank you very much.
Okay, we'll have a break up till 7 o'clock and then we'll